MCT4C, we're on day 7 of polynomial functions, evaluating polynomial functions. I would like to just take a minute to go over some of what we did yesterday because it was a lot. So let's look at f of x equals x to the 4th minus 13x squared plus 36. So we know that this is an even degree quartic. It is positive because a equals 1. It's invisible, but that gives us the information we need from our chart, that as we look to the right, then our function will go up, and as we look further and further to the left, our function will continue to increase. So we know something about the behavior on either end. We know the domain. For an even degree positive polynomial, the domain will be all x is a real number, and the range will have y larger than or equal to its minimum value, which we can call k. The degree specifically is 4. So that means we can have up to 4 x-intercepts, and we can have up to 3 turning points. Now, if we have some factoring skills, I'm going to write this in factored form, and we can verify these results. That, in factored form, would be x squared. For my lasts, I need to multiply to positive, add to a negative, so I'm going to have 2 negatives, and they would multiply to 36, add to minus 13, 9, and 4. So my first step is treating that almost like a quadratic, and then I will factor each difference of squares. Oh, don't worry, you get to do algebra. X plus 2, x minus 2. So when it is fully factored, we can see that we do have 4 x-intercepts, and they are specifically minus 3, 3, minus 2, 2, and they all are of order 1, which means that they are not turning points. So we have a sense of what this looks like. We have x-intercepts at minus 3 and 3, minus 2 and 2. It's going upwards as we go to the right, upwards as we go to the left, and they are not turning points, so I must do that and that. I have a y-intercept of 36, and if you would forgive my scale being so poor or so uneven, then we have a function that looks like that. Let's look at another example. If f of x equals minus 3 x minus 2 squared x plus 1, I know a lot of things about this. First of all, my leading coefficient is a negative. I know that I have an odd degree cubic if I were to expand that. And I know with negative odd degree polynomials, I know that as I approach infinity to the right, my function will decrease. So as x is going to the right, my function is going downwards. As I move towards the left, my function will go upwards. I know my domain and range. For an odd degree, negative, x can be any real number, y can be any real number. I know for a cubic, I can have up to 3 x-intercepts. I can have up to 2 turning points. And since this is in lovely factored form, I know that specifically I have x-intercepts of -1, 0 from this, which has degree 1, which means it is not a turning point. I have an x-intercept from this bracket of 2, which has order 2, which means it is a turning point. Let's draw a quick sketch. So my x-intercepts are -1, 0, 2, 0. If I do the algebra on that, I'm going to get a y-intercept of -12. I substituted a 0 in there, and that's what I got. So I have that. I know that I move to the right, it's going to go downwards. As I move to the left, it's going to go upwards. So I know the end behavior. I know at 2 I have a turning point, so I should have graphed that turning there, but the -1 is not. So at -1 we're going to come down through the -12 up to the 2 and turn around as an x-intercept and turn back downwards. They're a little ugly, but boy, we can sure graph in a hurry. Next example, a little bit new. Consider f at x equals x cubed plus 2x squared minus 3x plus 1, and we would like to evaluate the polynomial for x equals 2. We are looking for f at 2. So I am putting the value 2 wherever there's an x. 2 cubed plus 2 times 2 squared minus 3 times 2 plus 1. If I could give you any hint at all for these, is to just be careful of your order of operations, that we would have to do the power first and then multiply by 2. So that can cause hiccups. First we have 8. We have 2 times, I'm doing the power first, which is 4 minus 6 plus 1. So I have 8 plus 8, take away 6, plus 1, I have 11. Evaluate the function. For x equals -1. Same thing, be careful with negatives, make your brackets your friends. So we are looking for f at -1. I put a -1 in place of every x, plus 2 times -1 squared, minus 3 times -1 plus 1. Every -1 that I substituted into that equation, I put in brackets. You can just make us careful to avoid errors. -1 cubed is a -1. -1 squared, which is what I need to do first for this term, gives me +1, and 2 times +1 is going to be a positive. -3 times -1 is +3 plus 1. Just be careful. -1 plus 2 plus 3 plus 1 is 5. F at -1 is 5. That means for the function f at x, there is a point, -1, 5, and there is another point at 211. And we have done that by substituting by hand and calculating to find some points on that function. To verify, we're going to use technology for the same function. We're going to look if x equals 2. We know what our value should be. Let's look at -1 again. Make sure we did our calculations right, and x equals 5. We're going to use a graphing calculator. We're going to try this two different ways. The first thing that we're going to do is type the function into the calculator. So I have gone to my function button, and I need x cubed, so this right here is where I find my x. I'm going to cube it, so I need to the power of, which is this little hat, to the power of 3. So that is x cubed, a little odd looking, plus 2, I need an x again, squared, which I've got a nice button for that, sorry, right there, minus 3x, subtract, careful, your subtract button is here, not at the bottom, so I want this blue subtract button, 1. Let's see that we can see that clearly on our graph. I'm missing something, minus 3x. There we go. Subtract 3x plus 1. There we go. Graph. There is our function. At x equals 2, we can go to the table. First of all, we can trace and follow along when x is 2. And you can see down below that that is not terribly accurate. We can get a bit of a sense, but it's not terribly accurate. So let's go to the table. Table is up above the graph button. It's a little bit shiny for me right now. There we are. Table, second function, graph gives you the table, and it gives us all of our values. If I scroll down to x equals 2, I have my value 11. There we go from the table. F at minus 1, according to that table, I would have to go backwards, so scroll upwards, is 5, which is what we calculated. When x is 5, it's 161, and I wouldn't want to be doing that. Let's write that down so you've got a record of it. We went to table after we had typed our equation in to the function button. Second way of finding that information is going to the calc, which is up above the trace button. So right here, second function trace, I've got calc. And if I'm looking for value, which is the first option, so I'm going to hit number 1, I can just type in any specific value. So if I type in x equals 2 and enter, I will get my y equals 11. So I can get the same answers. F at minus 1, calc, -1. Careful, I used the negative. Negative for -1 is down here, not the subtract button. Enter, 5. So those are two options you can use, calc or table, to evaluate polynomials. Let's just solve a problem together. This is out of your text actually, page 97, number 10. We're going to use technology to help us solve it. David is designing a rectangular storage box that is lidless. He plans to construct the rectangular box from a 25 by 35 centimeter piece of cardboard. To me, a picture's worth 1,000 words. So he started with 25 by 35 centimeter piece of cardboard. And he's cutting equal squares of side length x from the corners and folding up the sides. So he is cutting out a square here and a square there. And because David is a mathematician, he uses the letter x, and he is cutting out x by x squares, all the same, whether my drawing looks like it or not, out of the cardboard. So that's the scenario we have. The volume of the box can be modeled by the polynomial function v of x equals x times 25 minus 2x times 35 minus 2x, and that is because along the sides we used to have 25 centimeters here, but when he cuts out this section and folds it, it will be shorter. It will be 25 minus x, and another x is 25 minus 2x. And the length, likewise, will be 35, what it used to be, subtract 2x. And then he will fold right along these lines. 25 minus 2x, 35 minus 2x will be the base of his box, and he will fold these sides up in the air. We'll have a height of x. So here is your height. Here is your new width. Here is your new length. And that's why the volume, I'm going to write it a little bit clearer. Vx equals the height times the width times the length. The first thing that question number 10 asks us to do is to graph the function using a graphing calculator. So I'm going to type this function in just like I see it. X bracket 25 minus 2x, and it's 25, it's the subtract on the right side, not the negative at the bottom. Oddly enough, that is a big problem with these silly calculators. 25 minus 2 times x, bracket, left bracket again, 35 minus 2x, close the brackets, and that is my function. Now if you hit graph, you won't see very much. In fact, we don't see a thing because our windows aren't working for this word problem. We need to change our windows to fit our domain and range. Our x values are the possible length that we can cut out of the corners of that box. The smallest that we can cut out of that box would not be negative. That doesn't make sense for a length. So I'm going to change my minimum for the domain to be 0. And my x max would be if I cut out the entire corner of the box, which would be just silly. Try and draw it on here. If we cut, nope, it's not working. It's all right. If we cut out half of the width, which would be 12.5, we wouldn't have anything left to fold up. So the maximum that I could cut out would be 12.5. I just made it 13. The y minimum and the y maximum have to do with the volume. The y minimum would be 0. The y max would be the maximum volume. And we're not sure what that is right now. So we're going to put in a large number, assuming that that could hold a very large volume. Let's go with 2,000. And if we can't see very well, we're going to adjust our windows again. There is our graph. The second question that the textbook asks, so that was A, was to graph it. It will let me. B is to find the volume when the length that you cut out of each corner is 10 centimeters. So they want to know what is the volume when the part that you cut out is 10 by 10. So I want function notation v of 10, but we can use a graphing calculator for this. We can use the calc or the table. I like the table because I can see it all at once. So second function, the graph button has table above it, and I'm going to scroll down to when x is 10. So when x is 10, our volume is 750. They ask us to verify that by hand. I'll let you do that. Using the graph, we're going to determine the size of the square that should be cut from the corners if the required volume of the box is 1875. So for D, they're asking us, what is x when the volume is 1875? Well, I can find that on my chart. There it is. Whoop. When my y value is 1875, my x value is 5. Volume at 5 is 1875. And that saved me a lot of work by hand. Please try page 95 to 97. Doesn't like having so many things on. Page 95 to 97. Numbers 1 to 13. 1 to 13. There we go.